That's exactly what this is. What happened is the model started to converge to what it needed to, meaning the weights, a little faster than it was able to update the intrinsic representations of some of those states. And by the time the model solidified, if it moved those internal states a little closer, even though it needs to get over here or over here somewhere, en route to there, it gets blocked by it saying, hey, it's not like these poses, it's only like those poses, but it can't get past the local optima because we're using gradient descent. So how do you solve that problem?
Restart with a different seed?
Yeah, that's the solution I'm going to recommend, is just restart with different seeds until you don't get too many of them. You might have to do it 4 or 5 times. Don't waste your time doing it 50 times trying to get 0 outliers. I don't care if there's a couple of them. They won't throw off your results very much, but they do throw off your results. Few alternatives. You could say that if they're farther away from the midpoint, the average point of all your data, if they're in, say, the upper quantile, if they're, how would you code this up? If you can come up with some heuristic that identifies which ones are probably outliers, and one way to do that would be measure their distance from the centroid of your data. Maybe if they're in the top 90%, you might every once in a while just try randomly restarting them to be at the location of another random point. That's kind of a hack, isn't it? Nevertheless, it works just fine. I did it, and that got rid of them all. If you want to implement some kind of a hack to get rid of those outliers, cool, go for it. If you're feeling lazy, just do a few random restarts until you get decent results. If you have 3 or 4 outliers, or even 7, good enough, turn in your results, I'll accept it. And if half of the thing is splinched in 2 ways, try a different random seed, because that'll totally screw up your results. Yeah?
Which type of tools do you generate?
How did I plot it? I used my own code for plotting stuff, because that's kind of my way. If you, was it assignment 3? Remember this code? I provided an svg.h in CPP, and here's some example usage of it, and it generates plots like this. This is what I ultimately wrote I wrote a little program that plots dots and draws lines, and I thought this was a very useful way to automatically generate them. Usually what people do for this assignment is they will just print their results to standard output. They'll paste it into Excel, they'll plot it with Excel, and they'll get a bunch of points, but they won't be connected with the lines. If you do that, is that good enough? We'll say yeah. In my opinion, that's a little bit wimpy. You should be able to generate a decent looking plot just by virtue of, hey, you're grad students and this is important proficiency, but it's not really part of this assignment. So if you plot it in Excel and then you can see this kind of organization, you can tell it has the same structure, I'll say, yeah, it's right on, you've got credit. Yeah. There's lots of tools out there. If you want to learn one, the Waffles Machine Learning Toolkit is what I wrote. You can download that. It has a tool in it called Waffles Plot. And one of its commands is scatter. And the Waffles Plot scatter tool generated this one. So you just put your data into ARF format, and then with some commands to the Waffles Plot scatter tool, you can generate it to look exactly like this one if you feel inclined to learn the tools I wrote. Not required. Writing your own SVG one would be really awesome, or hacking together some other visualization system would be a great thing to do. Pasting in an Excel is the bare minimum acceptable level of fine, I'll accept it begrudgingly. But that's okay, because you're not graded on my opinion of it. You're graded based on, did you achieve the correct results?
So in the waffles thing, how do we get, like, are there commands for the colors and the lines connecting only, like, adjacent points?
There is, let's see, github.com/mike-gashler/waffles. Okay, so I went to GitHub, I followed the link to the website. Here's documentation for the waffles plot tool. This is generated man page-like doc stuff. I'm going to search for scatter. So you're going to say waffles plot space scatter space, and then what do you do? Oh, in fact, by default, when you're making a scatter plot, it always connects the sequential points. So it'll do that automatically. Color X data Y, you're going to pass in here the color, which you're going to use the word row for, meaning that the row in your data set indicates the color for it to plot by. Data is going to be the name of your output file, the ARF file that you output. And then X is probably going to be the number 0 and Y is the number 1. These are the columns of your X and Y axes to plot the points at. So here, let me spew this out for you really fast, just since you asked. The command is going to be something like waffles plot scatter then you're going to say row state.arf01 and pipe that to myplot.svg. Something like that will plot an ARF file containing a bunch of points and we'll connect them. By putting row in this color slot, it'll use the spectrum like you saw in those pictures. And then there's a bunch of flags you can add to adjust the size of the dot and the thickness of the lines and the size of your chart and things like that if you want to look into it. Not the world's greatest plotting tool, but it's the one I wrote because I needed one. Okay. Any other questions on assignment 6, or do you feel comfortable doing that this weekend? Yeah.
My presentation has some gray area.
The frame. Okay.
Well, what's the reason?
The frame. I guess I don't know what you mean by the frame. Do you mean when you're generating these images, there's little pieces of it that end up being gray?
Yes.
Ah. What usually causes that is this. Your neural net, you're going to be training on values between, so in the original image, you have values between 0 and 255. You're going to divide them all by 256, and then now you have a bunch of values from 0 to almost 1. And then you train your neural network on that, and then you make predictions, and usually it predicts things between 0 and 1, but sometimes it's going to predict things slightly smaller than 0, or maybe slightly larger than 1. If that happens, and then you multiply by 255 to generate the pixel values, you're actually exceeding the range supported by the channel. This will cause funky looking colors that kind of border the edges in your images. So what you need to do is clip the values so they're the max of 0 or the min of 255 and the predicted value. So you clip it into the range you want and then plot it into your pixels, and then that will then it will look good. I'm guessing that's what the problem is. I could be wrong. But if, yeah. I don't know why it would be gray. Usually it makes bright yellows or funky reds or little speckles of colorful things around the edges there. Yeah. Okay. Oh, wow, time flies. What else? Can I cover that today? Oh, let's talk about autoencoders really fast because it's highly related. fact, I'm going to reuse this picture because I feel like I've talked about autoencoders in this class. Have I not? Well, let's do it really fast. Imagine a two neural network system where I'm going to feed x into it, and I'm going to compute x. First of all, why, right? I mean, who would need two neural networks to compute the identity function when we already know the identity function? It's just a matrix with ones down the diagonal. But there's something interesting here. Let's suppose x is large, like, say, 4096 dimensions. And let's suppose v is small, like, say, 2 or 3 dimensions. We're essentially ramming our data through a bottleneck and then trying to recover our original data. What's this going to force the neural network to do? Yeah, it's going to have to somehow encode whatever's in x into 2 dimensions and then figure out how to decode it. And so this actually turns out to be a useful thing to do. And when you train a neural network in this way, we call this model the encoder, and we call this model the decoder. And the whole model, when they're put together, we call an autoencoder, because it automatically learns to encode x into something and decode it. And then you end up with 2 pieces. Do you see that this one is the exact same as the one I'm calling the observation function in assignment 6? It's a decoder. This one has no place in assignment 6. There is no encoder in assignment 6. And in fact, we kind of are doing assignment 6 by training only the last half of an autoencoder. But we're doing it in kind of a funky way, because usually with an autoencoder, you only go forward. By which I mean you only feed forward, and then you backpropagate and update your weights. But in the inference approach, the way we're doing it in assignment 6, is we're pretending we only have this much of an autoencoder, and we're using forward prop to and then back prop to update the weights, but we're also updating the v's by backpropagation, which is kind of the backwards way that an autoencoder does it. Okay, which is better? Inference, which is where we figure out what values are needed here in order to arrive at the values that we got, or an autoencoder, which learns the whole process in an up-down approach. Well, clearly inference is better because I'm making you do it. But that's a bad answer. How would you compare these two approaches? Interestingly, autoencoders are a little bit more stable. Inference has the ability to take V's that are kind of related and splinch them off in separate directions. In fact, those outliers that we were getting, that I pointed you to, that are the problem of this assignment, those don't happen if you use a big autoencoder to do it. However, autoencoders have some problems. They don't converge nearly as fast. They have this extra model that needs to be trained. You have to backpropagate farther, so it's as though you have a larger, deeper neural network, which means exponentially longer to train. And also, they have this issue of, we can't really do a 1-pixel camera right here because autoencoders assume you're feeding in the same thing as you're predicting out. Whereas with this inference approach, I could feed in my pixel coordinates, or my attention, into here and predict just a single pixel. And you can do some stuff with the inference approach you can't quite do with an autoencoder. So these are two highly related, very similar techniques, but they're not exactly the same thing. An autoencoder uses 2 parts. We're doing it with just 1. There's a fun test that was done with an autoencoder that I kind of like, so let me describe it here. It looks like this. We used 8 values, 3, 4, 5, 6, 7, 8. Pretend those are nice uniform circles. For the input and output, and just 3 values for the bottleneck. And we're going to feed to it a number from 0 through 7 by using the a one-hot encoding. So let's suppose this is 0. Why am I red? Let's go black. 1, 2, 3, 4, 5, 6, and 7. Got a little off here. Okay. So imagine that only one of these circles is going to be hot and all the others are going to be set to zeros. And we're going to feed it through. So if we're doing the number 4, then this one will be activated or be outputting a 1 and all the others will output a 0. And then we train the autoencoder for a long time. What do you think happened on these internal units? Yeah.
Binary?
Yeah, except it wasn't human binary. It was weird binary. So the reason we did 8 to 3 to 8 is because 2 to the 3rd power is 8, right? So you can see what we already knew what we wanted it to do. We were trying to get it to do it, and it turns out it actually works. But it has to find some encoding here that enables it to remember what it had and be able to decode it again. And the machine basically invents its own language such that every possible case of one of these being hot results in some encoding here that uniquely represents it in a binary type language. And you can do this experiment yourself. It's kind of fun to see your neural net invent binary. And it'll never correspond with the way we do it, where 0, 0, 0 is a 0, and 0, 0, 1 is a 1, and 0, 1, 0 is a 2. They'll always be distributed however it sees fit. And it has something to do with the way you randomly initialize the weights and how the order in which you presented the patterns and whatever it started settling on. But the encoder and the decoder will eventually learn to agree with each other in such a way that it both encodes and decodes the values. And it's just kind of cool to see it invent its own alien language. Could 2 neural networks develop a language and start talking to each other? Could this evolve into a society of neural networks? I don't know, but it's fun to think about. Anyway, here were a few unsupervised learning techniques. Thanks for coming today, and see you next time.